sp3d2 hybridization. sp3d2 hybridization. This is another important hybridization. When one s orbital, 3 p orbitals and 2 d orbitals, one s orbital, 3 p orbitals and 2 d orbitals mixed together or hybridized together to form 6 identical hybrid orbitals is known as sp3d2 hybridization. One s orbital, 3 p orbitals and 2 d orbitals, that is 1 s 3 p, 5 plus 2 d orbitals. 1 s 3 p, total 4 plus 2. So 6 orbitals are involving. So that will form 6 hybrid orbital. 1 s orbital, 3 p orbitals, 1 plus 3 4, and 2 d orbitals, 4 plus 2 6. So these 6 orbitals are take part into hybridization. So that 6 hybrid orbitals will be formed. This type of hybridization is known as sp3d2 hybridization, and the orbitals are called as sp3d2 hybrid orbitals. These sp3d2 hybrid orbitals, out of 6 orbitals, 4 orbitals are in one plane like this. 4 orbitals are in one plane and other 2 orbitals are perpendicular to this. So that here the bond angle is 90 degrees. These 4 are in one plane and other 2 are perpendicular. So the total as a whole the bond angle will be 90 degrees. This hybridization is called as sp3d2 hybridization. One s orbital, 3 p orbitals and 2 d orbitals mixed together to form 6 identical hybrid orbitals is known as sp3d2 hybridization, and the orbitals are called as sp3d2 hybrid orbitals. Example, SF6, sulfur hexafluoride. Hexa stands for 6, fluoride. Sulfur hexafluoride. Sulfur hexafluoride. So in sulfur, the central atom is S. The central atom is S. Its atomic number is 16. So electronic configuration is neon 3s2 3p4. That is, in the valency shell we have 2 electrons in 3s orbital and 4 electrons in 2p orbital, 3p orbital. 1, 2, 3, 4. So here 2 half-filled p orbitals are present. The valency of this sulfur is 2 in its ground state. Here 3d orbital is also there, but it is empty. On first excited state, this p electron will enter into d orbital. So the electronic configuration is 3s1, 3p3, 3d1. This is in first excited state. This is first excited state. So, sorry, 3s2, 3p3, 3d1. The 4 electron will enter into here. 3s2, 3p3 and 3d1. Here another pair of electron is there and empty orbitals are there. So on second excited state, here according to these 4 unpaired electrons are there, in this first excited state, the valency of sulfur is 4. And second excited state, this s electron will also enter into 3d orbital. So on second excited state, the electronic configuration of sulfur is 3s1, 3p3, 3d2. There is no change in the inner valency, or in all the cases it will have same neon configuration. Don't get confused. There is no change in the inner electron, only valence electronic configuration will change. So here now we have 1 electron in 3s orbital, 3 half-filled p orbitals and 2 half-filled d orbitals. Now total we have 6 electrons in the valency shell of this sulfur. Here valency is 6. This is second excited state. So in this state, sulfur will undergo to this sp3d hybridization to form 6 hybrid orbitals. So that each hybrid orbital is filled with 1 electron each and they are in a position to form sigma bonds. So each sulfur atom, now here we have 6 hybrid orbitals. 4 orbitals are in one plane and other 2 orbitals are perpendicular to this, so that you have 6 hybrid orbitals. All hybrid orbitals are filled with 1 electron. Now in fluorine electronic configuration we know 1s2, 2s2, 2p5. That means 1 half-filled p orbital is present in fluorine. So the half-filled p orbital of fluorine overlaps with half-filled sp3d2 hybrid orbital of sulfur to form s-f sigma bond. Another bond will be formed like this. Here you find one more. So that sulfur can form 6 sigma bonds with 6 sulfur atoms. That's why in SF6 molecule you have 4 S-F sigma bonds which are in one plane. This is one plane with 90 degrees and other 2 are also like this. That means one sulfur is here, one fluorine, other fluorine, in fluorine, 4 fluorines are like this. They are in one plane. One F bond will be like this. So if here you have one fluorine, on 4 corners you have 4 fluorines, so you have 4 faces. And in down also you have 4 faces. That's why the shape is said to be octahedral. Octahedral means 4 faces. For this molecule, 4 faces. These are 4 faces upwards and 4 faces downwards. Total 8 faces are there. Octa means 8. So this molecule is in octahedral shape. Here also, in the valency shell of sulfur, in SF6 molecule, 6 pairs of electrons are there. That is 12 electrons, 4 electrons more than octet. This is also an example for extended octet. This is another good example for extended octet. VSEPR theory. VSEPR theory. This is valency shell electron pair repulsion theory. Valency shell electron pair repulsion theory, simply called as VSEPR theory. The necessity for proposing this theory is certain structure of certain molecules cannot be explained by valency bond theory as well as with theory of hybridization. To explain the structure of such molecules, this theory was proposed. The necessity of this theory was arised when there are some non-bonding electron pairs present in the valency shell of a central atom. If one or more non-bonding pairs of electrons are present in the valency shell of a central atom, the bond angles and shape of the molecule is not coincide with the angles that are present in the hybridization in which the central atom is involving. For example, if we take the structure of NH3. In NH3, according to this formula, the central atom is nitrogen, that is the atom which was connected to other atoms is nitrogen. So the nitrogen atomic number, if you observe, it is 7. So its electronic configuration is 1s2, 2s2, 2p3. This is the valency shell. Now in the valency shell of nitrogen you have 2 electrons, and in 2p orbital you have 3 electrons. That is 3 half-filled p orbitals are present. 3 half-filled p orbitals are present. Suppose here, if only p orbitals are take part into the bonding with 3 hydrogen atoms, we know that 3 p orbitals are perpendicular to each other. Without hybridization, if 3 p orbitals are directly involved in the covalent bonds, then what happens? The bond angle must be 90 degrees. And they should be in a T shape or in some other shape like that with 90 degrees angle. But if you observe the structure of NH3, the X-ray studies of NH3 shows that NH3 molecule is in pyramid shape and the bond angle is found to be 107 degrees 30 minutes. They are in pyramid shape. The structure is in pyramid shape. So if pure p orbitals are directly involved in the bonding, we cannot explain this structure. Suppose if this was involved in hybridization, what type of hybridization it has to be involved? We have sp3 hybridization. If sp3 hybridization is there, the molecule should be in tetrahedral shape with bond angle 109 degrees 28 minutes. If it is sp2 hybridization, 120 degrees bond angle. If it is sp hybridization, 180 degrees bond angle. If it is sp3 dehybridization, 90 and 120. If it is sp3d2, 90. None of those bond angles are coincide with this bond angle, that is 107 degrees 30 minutes. But this hybridization is nearer to sp3 hybridization, which is 109 degrees 28 minutes, just 2 degrees, almost 2 degrees less than the tetrahedral shape or sp3 hybrid orbitals. Now, if nitrogen is in sp3 hybridization, now how can we explain this? How can we explain the deviation of the bond angle? For that purpose only, this valency shell electron pair repulsion theory was proposed. According to this theory, in the valency shell of central atom, we have certain pairs of electrons after bonding. Now, there will be a repulsive forces which pushes the electron pairs away from each other, because all are like forces. Around the central atom, some repulsive, some negative forces, negative charges are accumulated or concentrated. So there will be a repulsion between these electron pairs. If all pairs are involved in the bonding, the repulsive forces are same. So those molecules in which all pairs are involved in bonding will have same bond angles in their molecules also. But in some molecules, some pairs are involved in the bonding and some pairs are not involved in the bonding. In such molecules only, the deviation in the bond angle was observed. Taking those all observations, they proposed that there will be a repulsion among the electron pairs. These repulsive forces are not equal, and they are in the order of the repulsion between non-bonding. The repulsion between non-bonding is greater than non-bonding dash bonding is greater than bonding dash bonding. Non-bonding is greater than non-bonding, and bonding is greater than bonding and bonding. Due to the difference in these repulsive forces, there will be a deviation in the shape of the molecule. That's why the bond angles are deviated from the angles that was present in the hybrid orbitals. Now let us discuss the structure of this NH3 in the light of this VSEPR theory. Now in NH3, the valency electronic configuration is 2s2 2p3. Now if nitrogen is involved in sp3 hybridization, it will form 4 hybrid orbitals. 4 hybrid orbitals. Now in the valency shell of nitrogen, we have 5 electrons. 5 electrons are there, but orbitals are 4. So when these 5 electrons are distributed in all these hybrid orbitals, what happens? 1, 2, 3, 4 and 5. So 3 hybrid orbitals are filled with, are half filled with 1 electron each, and 1 hybrid orbital is completely filled. Now in the formation of bonding, only half filled atomic orbitals will take part into bonding, but not the filled electrons. So here let it be like this. The half filled atomic orbital of sp3 hybrid orbital of nitrogen will overlaps with half filled 1s orbital of hydrogen, and by mutual sharing of a pair of electrons forms N-H sigma bond. And another hydrogen atom overlaps here, and by mutual sharing of a pair of electrons forms another sigma bond, and third hydrogen will form third sigma bond. So that nitrogen will form 3 sigma bonds with 3 hydrogen atoms. And this pair is a non-bonding pair. Now in the valency shell of nitrogen, we have 4 pairs of electrons. Let it be. There are 4 pairs of electrons around the valency shell of, in the valency shell of nitrogen. Around nitrogen atom, we have 4 pairs of electrons. 1 pair is here, other pair is here, third pair is here, fourth pair is there. Now there is a repulsion between this pair this pair, in between this, in between this, in between this. But the repulsive forces with non-bonding to bonding is more when compared to bonding and bonding. That's why the bond angle, it was pushed. The bond angle was decreased nearly 2 degrees. That's why from 109 degrees 28 minutes to 107 degrees 30 minutes, the decrease of bond angle is observed in NH3. The decrease of bond angle is due to the presence of a lone pair of electron in the valence shell of nitrogen. His other 3 pairs are bonding pairs, and this pair is a non-bonding pair. The repulsion between this pair and these pairs is maximum than these pairs. That's why the bond angle was decreased from 109 degrees 28 minutes to 107 degrees 30 minutes. And the molecule is in pyramid shape. In the light of this VSEPR theory, H2O is a well-known water molecule. In H2O, 2 hydrogen atoms are bonded with oxygen with a covalent bonds. The X-ray studies of this molecule shows that the bond angle in H2O is 104.5 degrees. Now let us see how this H2O molecule is forming. If we observe the electronic configuration of oxygen, oxygen's atomic number is 8. So its electronic configuration is 1s2, 2s2, 2p4. So in the valence shell of oxygen, we have 2 electrons in 2s orbital and 4 electrons in 2p orbital. That means 2 half-filled p orbitals are there. These 2, we know that 2 p orbitals are perpendicular to each other. They are with 90 degrees. But here the molecular bond angle is said to be 104. So if pure p orbitals are directly involved in the bonding, the bond angle should be 90 degrees or nearer to 90 degrees. But here nearly 14.5 degrees deviation was observed. It indicates that pure p orbitals are not directly involved in the bonding. Then what happened? This 104.5 degrees is nearer to sp3 hybridization, because the angle in sp3 hybrid orbitals is 109 degrees 28 minutes. So slightly 5 degrees deviation here we are observing. So let us try to explain this structure in the light of this VSEPR theory. Now let us consider that oxygen is involved in sp3 hybridization. If it was involved in sp3 hybridization, what happens? 4 hybrid orbitals are formed. In the valence shell of oxygen, we have 6 electrons. 1, 2, 3, 4, 5 and 6 electrons are there. 2 orbitals are filled with 2 electrons each, and other 2 orbitals are half filled with 1 electron each. Now this sp3 hybrid orbitals of oxygen overlaps with half filled 1s orbital of oxygen, hydrogen, and by mutual sharing of a pair of electrons forms O-H sigma bond. So that one O-H sigma bond is formed here. And another hydrogen atom overlaps here to form another bond. So another O-H sigma bond will be formed. Now other 2 orbitals are fulfilled. That's why they won't take part into any type of hybridization. Now in H2O molecule, around oxygen atom, we have 4 pairs of electrons. 4 pairs of electrons. This pair is due to the bonding of hydrogen, and these are non-bonding pairs. 2 pairs are non-bonding pairs and 2 pairs are bonding pairs. According to VSEPR theory, the non-bonding repulsion, that is the repulsion between these 2 pairs, is more than bonding and non-bonding, than bonding and bonding. Because of the presence of 2 non-bonding pairs in H2O molecule, A greater decrease in bond angle is observed. In NH3, just 2 degrees decrease is observed. Here nearly 5 degrees decrease is observed in H2O molecule. So that the molecule is in V shape with an angle of 104.5 degrees. This is the shape of H2O molecule.